Just because a museum HVAC system is designed for tight climate control doesn't mean it can't be adjusted to the new paradigm. We find that slightly wider ranges for allowable relative humidity have a significant impact on energy consumption, but how much? So our presentation illustrates this and what the results can be. So there are plenty of ways to save energy and carbon by spending money on your systems. You could completely replace or build a new mechanical system. You could replace parts of your system like new fans or new coils or new chillers. Or you could surround your building with lots of insulation, try and save energy that way. But all of those methods take a lot of time and money. The alternative is just to adjust the thermostat. Sit down at your computer and make adjustments in the controls so that you accept the idea of slightly wider ranges for temperature and relative humidity. And that doesn't need to cost anything. And we want to show you how much it can save. So one of the challenges we found is that it's difficult to go to a museum and say, look, we'd like to do a bunch of tests and figure out how much energy we save if we run your systems differently for the next several years. But we found in previous conferences of this group that people want to see data. So luckily, Keith has worked with several museums over time and has been able to use that experience to basically create some computer models in this particular case, we're using two museums. So the older museum is one that was built prior to 1930. It has thick masonry walls and no insulation. And this is a building type that's very common both in North America and in Europe. So we think it's a good model to use for a portion of the study. Then there are also plenty of newer museums that were built, say, after 1980. And most of these have thinner walls, less mass, but they do have insulation and a vapor barrier. So we figure, and that kind of museum has been built all over the world. So Keith created two computer models using his experience with those kinds of museums in order to be able to input information and then see the results based on different kinds of behavior. So we have two museum types, and then we put them in 4 different locations so that we could see what kind of influence climate would have on energy consumption. So in North America, we picked New York and St. Louis, where he and I are, but then also Mexico City, which has a quite distinct climate, and then also Amsterdam in honor of Art Switch, and to make sure that we had an example in Europe as well. And then, so for those 2 museum types and those 4 locations, we set 4 distinct sets of climate control parameters. So the baseline at the top is the old paradigm, basically, 70 degrees or 21 degrees Celsius, plus or minus 1 degree Fahrenheit, and then relative humidity of 50% plus or minus 2%. And you might think, my God, that's so tight. But what we found is that plenty of museums, even if they're designed to run a little more fluidly, often run at this very tight rate. So we use that as our baseline. Then for the 3 conditions that we looked at that get progressively more relaxed, the first one, all we did was allow the relative humidity to fluctuate more. So in condition 1, the set point for RH is 45% plus or minus 5%, and we kept temperatures still tight. Then in condition 2, we still did the RH fluctuating plus or minus 5%, but we adjust the set point seasonally. So in winter, the set point would be 45, and in summer, the set point would be 50. This kind of seasonal ramping allows the system to run in a way that's not fighting the outdoor climate as much, but it's still providing the collections with relatively tight controls of only plus or minus 5%. Then finally, for condition 3, we did the same thing for relative humidity with a seasonal set point and 5% plus or minus, but we opened up the set points for temperature as well. So the plus or minus for temperature is still tight, but we shift from winter to summer from 68 degrees to 72, or in Celsius world from 20 to 22. So that way we're still really giving the art very tight controls and making the seasonal adjustments such that the painting is not going to stretch. The thermal impact of what's going on temperature-wise is not going to be an impact. So And Keith took all of these data points and ran the systems accordingly. And with that, I'm going to hand it over to Keith. Should I stay on this slide or move to the next one?
Yeah, no, go ahead and stay on this side, but thanks, Sam. Like I said, now go ahead and step in for that dry engineering data analysis portion of what really, no, go ahead and keep on the last one, I guess, for now, Sam. Of what happens when you embrace these approaches. Sam shared we're not really talking about, I mean, we have conversations going on within this actual conference, talking about the ability to move these temperatures and humidity set points with respect to the ability to continue to protect and preserve the art. What we're really focusing on here is what do these impacts look like? What happens when you do what we've all been discussing? And what I want to help you understand is what we're really building on is a unique relationship that we've been able to develop with several museums, particularly in my case here in the Midwestern region of the United States. In these relationships, we've got kind of a long-term partnership where we've actually worked with facilities and operations groups, and we're helping them optimize their system and control. And as part of that, we've developed detailed simulation models specific to art museums. So these aren't just a pretend prototype art museum. These are detailed simulations that we developed based off of specific buildings, their actual operating procedures. And then over time, we've been able to continue to calibrate these models as we partner with them for 6, 7, 8, 10 years, continue to calibrate the models to make sure that we can reflect the actual performance. And I'm sure those of you who work within an active facility can really appreciate why we do this. Because, a working museum doesn't really want us to use the functioning museum and the archives areas as a laboratory when we're testing novel ideas. But like I said, over the time, we've gotten these calibrated, and they've really, and we've matched them to utility bills to make sure we're confident. And so, like I said, we're very comfortable with what we're doing shows up in real life, because that's what we've used these models to do. I also want you to understand that these also represent, understand facilities that are very focused on how they can maintain their performance and the energy consumption. So these are probably better than average type facilities when you look at it, because the reason I've done this is they've been willing to invest in partnering with somebody like me to improve their operations. So Sam, we can go to the next slide.
Yeah, just a sec.
So simulating the performance of these buildings, as you can see, this condition, the baseline is basically how much energy is consumed under, in this case, the newer of the museums that we used, the post-1980s, early 90s construction. And even just simply relaxing the set points, as has been discussed many times, where you can have a humidity control between 40 and 50% instead of trying to hammer on that 50%. The impact is a reduction of real life reduction in your heating and cooling neat loads by approximately about 10% in that building. And understand that is simply representing changing the thermostat settings, changing that deadband. That is no capital improvement, no major other changes. And as we continue to move on to some of these other more innovative strategies, and many of which have been applied in museums across both the country and the world, where we allow the reset, a general reset over the summer to lower the, relax that set point and lower the pressure on the system. We can see savings just by opening these things up of north of 20%. That's really almost even doubles that savings again based off of doing that. Sam, up the next slide. We can look at these same adjustments, and when we carry it to an older facility, like Sam said, something that is more turn of the 20th century, that doesn't have that insulation, that's more indicative of a lot of the older museums, those same numbers actually hold up. We don't see quite as much of a change when we just stretch out that humidity thing on that condition 1. We're still seeing 6 to 7% in savings, but as we start to look at how we can reduce the loads over the seasons, it's still available that when we talk about cutting these energy loads, we are cutting to the tune of approximately 20%. Next slide. And as we look at where does that energy come from, it's very clear that while that we do reduce some of the energy used in the winter because we don't have quite the humidification load, the majority of this is going to be found in the summertime, the summer months, where we're relaxing that load on dehumidification. Next slide, Sam. So, we're in a world now where energy, BTUs or kilowatts aren't the only means of using as a metric, as of reporting numbers. And so we wanted to look at this from a carbon dioxide production standpoint as well, just looking at what happens when you make these changes. Now, what's reflected here is that third condition where we expand the conditions as well as allow it to creep a little bit in the summer and move the overall set point up in the summer. I also want to warn you, when we look at the carbon dioxide, we're changing our units a little bit to talk about total energy consumption. The carbon produced not just from the heating and cooling consumption, but also think lights, computers, everything else. And we do this to be consistent with industry norms. When we talk in the industry about the carbon consumption of a building, we talk about the whole building, not just heating and cooling. So as a result, the percentage reductions go down. In that newer museum, I only reduced the carbon by about 10%, but the absolute numbers obviously hold still because I'm just including more components in these things. But the important part is you see in both cases, the carbon dioxide emissions, the reduction, the impact on how much carbon we put in the facility is significant. You look at these numbers and you see that the older museum that we're using here is significantly higher. But what these are, again, these are absolute numbers. And that museum is about 7 times larger than the modern one that we're using and has a much higher energy intensity. So you're seeing that the potential carbon savings is, even though it's a less percentage reduction, it's about 10 times as much carbon is saved in that system. Next slide, Sam. But more importantly, we want to take a look at, hey, does this same concept, what happens when you start moving these buildings to multiple geographic climates where we have different types of climates and different types of impacts due to location? So one of the things we did was we took those same museums and relocated them, as Sam was saying, to New York, Amsterdam, and Mexico City. And why it may not be 100% fair, because, as a design engineer, I might tweak the system somewhat to accommodate those specific climates. This is still a very valuable exercise because the systems used in these buildings are really consistent with what you would see in most of these locations. And so you really can't see that the impact, why it does vary, whether I'm going from as I move to New York or Amsterdam or Mexico City, which has kind of a less energy intensity for provide its heating and cooling, that potential savings is still up there in that 20 to 25% range. And as I move into the older building, that number continues to show in there. Same, yeah, there you go. Where you see some of those types of things, in which case we can climb even as high as 30% as far as those as far as the energy savings.
It's also just sort of interesting here to note that in the case of the older museum, that the temperature difference, allowing seasonal set point of temperature makes not very much difference compared to RH.
And there is a reason for that, Sam, just to share with the group as far as that goes. And as you start to change the temperature, it does get a little more complicated, as a lot of these buildings, in order to hit that humidity, they effectively cool all the air up, and then they effectively are in a heating mode. We do all kinds of extraordinary things with designs of newer buildings to reduce that heating load. But the museums, most museums have to do a considerable amount of heating in their dehumidification mode, since they overcool the air to get the moisture out and heat it back up. So if you set that temperature up high and you haven't made other provisions, you don't save as much energy you'd think by raising the temperature from 70 to 72 or 74, because you've actually had to cool that air that's moving through the building and then reset that back up. So in order to gain those advantages, you really have to kind of redesign the system as opposed to just make the simple temperature adjustments as we're talking about. And I'm glad you brought that up. So looking at the next side of things, I also want to kind of convert this and kind of share with you guys that, we live in a world where, there's a second critical unit of measurement that we always fall back to. There's a lot of discussion of how do you get people to want to implement these ideas, because, real dollars come into play. And so dollars is a legitimate means to try to measure or understand what the impact of making these changes are. Again, we're using that baseline and that condition 3. As you saw, condition 2 and 3 are very similar in the impacts. And, we don't want to imply that dollars would trump an institution's charge to protect or preserve their collection. They never should. But when we begin to understand that we can effectively preserve our collections while relaxing these thresholds, you can see that the potential impact is pretty significant. We use that same analysis. We took the potential cost impacts of these strategies. Okay, stay back on the last one, Sam. We took these potential cost impact and looked at the total energy consumption, and we kind of prorated our museum over 100,000 square foot, so that you can kind of see prorate that up and down as you might have for different size facilities. But generally, the important things to note with these numbers is again, we're talking about total energy consumption. That's the electric bill and the gas bill coming into each of these buildings if the St. Louis building was located in these other places, as well as, like I said, being able to prorate them. One of the first things you're going to notice is in my particular part of the United States, you could say either we're blessed or we're cursed with very cheap energy. Even though we use more energy than most of the other scenarios, we face a blended energy rate for electricity for most of my clients around 6 cents a kilowatt hour. I mentioned this as a curse because it does impact our ability to motivate building owners or operation staffs to aggressively reduce energy consumption, because with energy so cheap in our neighborhood, the impacts are less. But even at that, these simple adjustments you can see on a 100,000 square foot building can easily reduce energy consumption by 50, and if we get to other climates, 60, 70, and $100,000. And again, as we're stressing, this is with very little capital investment. Sam, next. So the last thing I want to kind of share or follow up is, as we're doing this analysis, and as with the information we provided here, if any of you guys are like me, when I hear computer modeling or simulations, I always default to taking any data with a grain of salt. Someone who's performed these sorts of simulations, there's generally enough gray area that it's included that you can really impact the numbers or put your thumb on a scale. That being said, I want to share with you, we've taken a very conservative approach to these models, and our clients have really developed that level of trust that we can match or if not beat the projections when we work with them. To reinforce here, these are actually the utility consumptions of these two museums as we've worked with them over a period of 3 or 4 or 5 years of doing just control and set point modifications. Now, understand that why both of these facilities have dipped their toe into these changes we've discussed. They still haven't gone in, full in. And we're still working through some of the politics of trying to push more and more of these things in there. But so this is just a touch of some of these set point changes, and then some other corrections from a control or programming standpoint. But just by making some set point changements and control strategy improvements, you can see that the end result is, again, this is total energy cost. This is the bill coming into the museum, includes lights, includes everything else. Both of these places we're able to see that 20 to 30% reduction in energy just by trying to do smart things from how we control those. I've intentionally left off the parts where we've done capital improvements and had the big jumps as far as that goes. So with that being said, Sam, I'd like to throw this back to you to wrap up before we open up for any questions.
So yeah, I just want to make one other point, which is there are other ways to adjust mechanical systems to save even more energy. For example, reducing how much outside air is brought in, say at night when nobody's there, which we would heartily endorse. That's a little bit challenged now because of COVID. But in any case, we still thought that just purely by illustrating how much money can be saved without having to spend anything, that would hopefully help more institutions realize that it's an easy, straightforward thing to do, as well as one that's relatively low risk. And we've tried to leave enough time for some questions.
Thank you, Sam. Thank you, Keith. Seems like a very clear presentation. My first question is, with such easy results, and what do you advise to the best way to implement this? What are the holdbacks, and why isn't everybody doing this? Or how do you advise to change the mindsets?
Sam, I'll jump into that one and you can build on it if that's okay. But from my standpoint, like I said, most of the time I'm dealing with those guys who live in the basement of these museums or these facilities, and they're working hand in hand with those guys who wear those maroon polo type T-shirts and fix everything when things fall apart. and the guys who they work for. There is a struggle in that normally they, like I shared that in the previous breakout session, there's a level of empowerment that most of the facility and operations side of folks who see the energy bills or who see the impact on the energy coming in are not the ones, they feel that they've got things dictated to them. And so it's you've got that natural conflict between what they can do with their systems versus registrars and conservators and everybody who has their motivations. You need to get them all on the same page. And what's missing in a lot of the facilities is a champion that can get those folks together and be talking about it. When you get dollars that can say $100,000, suddenly might get somebody motivated to have a conversation at that point in time. Sam, you want to build on that?
Well, actually, I see that Patty Silence is here, and she has a lot of experience working with engineers and operators at her institution at Colonial Williamsburg. So Patty, why don't you shed some light on this too?
Hi, it's good to see you both. You do have to, I guess at my institution, I've tried to be that champion that Keith's talking about, and you do have to make friends with your facilities people, which everybody knows is a good idea anyway. I will say that most of our guys are afraid to make these changes without our blessing. They take their work very, very seriously of caring for the collection. And so, they might even be more rigorous than we conservators are, because we've been studying this now for, 10, 15 years and how we do want to widen set points. In our case, we have that very complicated programming. And so, we're heating all the time. We're not cooling in the summer. We're actually heating in the summer to get a lot of the wet Virginia moisture out of the air. But we have monthly meetings. You sit down together and you look at your charts and you say what's going right and what's going wrong and how you can fix it. We've had more success with shutdowns than we have with changing programming, because we pay a lot of money to a programmer to come in and change our program. Some of our buildings are set to a single point. They don't, it's hard to put a band on them even because of the original programming that's been put into them. And we have 600 structures that we're dealing with. So it's complicated.
I have another question about the airtightness too, actually, from James. If maybe in your research you've also included the different, taken into account any differing levels of airtightness in the two types of buildings you were looking at. And also, I don't know if we can link these two from Cecilia, the impact of COVID and the need to have air renewal more frequently in these museums. Is that something you can talk about?
Sam, you want to start with the air tightness? Because you and I fight that one all the time.
Well, you can
will
probably
too.
answer better in terms of how the model dealt with that. But in terms of COVID, yeah, it's very unfortunate that the simple way to address the concerns about having more fresh air for COVID is in direct opposition to sustainability. That one of the key ways to save money on museums and archives is to reduce how much outside air you bring into them, because that's where you're spending all your energy, is to get the outside air to be at the right condition. And you don't really need outside air at night, and you don't need as much. Most engineers have tended to design systems to bring in much more outside air than is necessary. So if you can restrict that, you're way ahead of the game. And if you do that, you'll save even a lot more money than what we showed you in this presentation. So with COVID looming as an ongoing kind of threat that people are going to be worried about, the choices are either to install ultraviolet filtration or other methods of filtering the air, or to just be more realistic about how much air change really is necessary. So, but Keith, why don't you answer the question about air tightness in the envelope?
Yeah, so as far as in the air tightness, and it is accurate, the older buildings that we have are not nearly as tight. It's that pre-1930s construction, rarely do I see anything what I'll call as a qualified vapor barrier that keeps the moisture in. And so we're trying to balance airflows coming in, and so we're not pushing it through the building. But that becomes a major challenge in there. From the perspective of this modeling, because we've used these models and we've calibrated ourselves by using energy bills over the course of a couple of years, we've gotten kind of those things baked into the cake with the simulations. But the reality is, there's also the impact of, I walk into one of these buildings and a lot of times there's the first conversation is what can the building actually hold because of that thermal or that hygrothermic or even that just air tightness as far as that goes. Most of these older buildings, we're not even talking about being able to hit the 50% humidity in the dead of winter when you're talking about a Midwest or an East Coast winter that gets down to 0 degrees. So, tightness is part in there. Like I said, something we always have to build into it. But these older buildings, it's just not something that's really baked into that cake. I mean, it is what it is nowadays, which is not that tight.